Hey friends, MoNaCo here. Feel bad. Got to make up for that really long lecture in video note 3 on half reactions. So I've got one that's like going to take about 3 minutes. Spontaneous reactions. So you're going to know how to use table J to tell if a reaction is going to happen spontaneously or not. And I guess the hardest part here in this lecture is, what does spontaneous mean? Spontaneous means if I just mix two things together, will the reaction go without any additional energy being put in? Spontaneous is like, whim, spur of the moment, just going to get up and go and do it. Okay? A spontaneous chemical reaction is one that will go forward with minimal addition of energy. Certain reactions are spontaneous because of the types of elements that are involved. Some ones are more reactive than others, and this tends to lead to more spontaneous reactions. Table J, the activity series, which we saw when we saw how acids and metals react, helps identify these spontaneous type reactions. So let's check it out. Table J and spontaneous reactions. General rule: elements above or higher on table J are more reactive than elements than below them. So elements higher on table J are more reactive than elements below them. A spontaneous reaction is a reaction that occurs without adding energy to the system. So usually these are exothermic reactions that have no activation energy. Now, if the single element is more active than the combined element, the reaction will be spontaneous. Non-spontaneous reaction will not occur unless energy is added to the system. So if the single element is less reactive than the combined element, the reaction will not be spontaneous. So we're going to look at these charts. So the single element versus the combined element is what we got to do. It says, so we're going to compare the single to the combined. If the single is higher up than the combined one, the reaction is spontaneous. Now, the opposite, when we compare the single element to the combined element, I think I wiped this by accident. Oopsies. There we go. If the single element is lower than the combined element, then it will not be spontaneous. So that's what we got to look at. So I'm actually going to have a reference table J out next to me because I don't want to be scrolling up and down all the time. So I got reference table J here, and I'm comparing the single element to the combined element, table J. There we go. So the single element is the zinc versus the combined element, metal, the lead. So I look for zinc on the chart, and I see that it's about smack dab in the middle. I look for lead on the chart, table J, and lead is 1, 2, 3, 4, 5, 6 steps below zinc. So zinc is more active than lead, more active than the lead. So it will react to form a spontaneous reaction. So complete the following by writing the products formed or no reaction. Since it is more reactive than lead, it will react. It will make zinc chloride and lead pure elemental lead, because zinc was more reactive. If it's more reactive, then it will sneak in and replace. So now we're going to compare the single to the combined. So zinc versus barium. Zinc, again, in the middle of the chart. Barium's actually above it. So since barium is already more reactive than zinc, zinc is less active than barium. So no reaction. The more active metal has already formed the compound. Putting zinc in there is going to do nothing to make the reaction go. This next one, calcium versus chromium. So calcium, the single element, versus the combined element. Calcium is actually kind of towards the top of chart J. It's only 3, 6, 7 down from the top. Chromium is about smack dab in the middle, 1 step under zinc. So calcium is more active than the chromium, so it will react to form calcium fluoride and chromium by itself. So notice we're just doing a straight swap of the elements. There's no balancing involved in these because they're nice and neat. Now let's look at manganese versus nickel. Manganese, Mn, bam, smack dab in the middle of the list, 1 step above zinc. Nickel's below it, so more active than the nickel. So if it's more active than the nickel, it's going to sneak into that compound and kick the nickel out and say, hey, you get out of here. Manganese sulfide and nickel pure. Iron versus magnesium. I think we're back to red now. So we're going to compare the element that's by itself to the one that's in the compound. Iron, where is it on the chart? It's about the lower middle. It's below chromium and zinc, so it's not as active as those. Magnesium, on the other hand, is above it. So iron is less active than magnesium. So we have no reaction occurring because the magnesium's already more active. It's already in the compound. Iron can't kick it out. It's not strong enough. It's not active enough to kick the magnesium out of the situation. Last one, cobalt and lead. I think back to green. So cobalt versus lead. Cobalt's kind of on the lower end of the spectrum, but lead is lower still. So cobalt is more active than the lead. So it's going to swap in, make cobalt chloride and pure lead elemental. So at this point, you should now kind of understand how comparing where the metal on the chart is will help you figure out if a reaction is going to occur. And that's really all I need you to know on this particular lecture. And I was trying to make up for the last one being kind of long. So you're welcome. A couple practice pack pages to try out for this particular topic on the activity series. Thank you for watching.